Well, welcome to the COM 1004 lecture. It's a great pleasure to introduce James Ridgway, who's one of my third year project students. And he's working on some very fascinating stuff to do with video steganography, which he's agreed very kindly to let us know about. Can I get out of the way, Claire?
Yeah, you can disappear now. Right, slight disclaimer. I don't know how long this lecture runs for. It's the first time I've given it, and I only finished writing it today, technically. So if it does look like it's going to go for more than the usual hour, 50 minutes, whatever, I will stop to have breaks because you won't want to listen to me talk for that long, and I also don't want to be talking for that long. However, I just want to start by showing you a sample of 3 clips. I've also given you should also have a questionnaire amongst you. So when I show you clips like this and there's different samples of stuff, I just want to perceive from you if you can actually notice information that's embedded in the video. So I'm going to start by showing you this, hopefully. The sound doesn't matter terribly for this first clip. Okay, so if you would be so kind, please indicate on the handout I've given you which one you think it is, but also, by a show of hands, who thinks it was encoded in the leftmost video? No one. From left to right?
That one.
Left? Who thinks left? Who thinks middle? Who thinks right? Right, so I'm guessing the rest of you think there's nothing hidden anywhere. Well, if you thought it was in the leftmost video, you'd be correct. Are my slides displaying? Sorry. Are my slides displaying properly? Ah, yes, they are. Brilliant. So, right. So I'm going to start with. I'm going to cover these topics throughout the course of this lecture. I'll kind of be ending with most of the demonstration stuff, and all of that is going to relate to basically the work that I've done as part of this project. So I'm going to start by discussing where steganography has come from, its origins, where you first hear of it, and some of the more primitive techniques and where you can find it in the literature. I'll then go on to discuss sort of like a general category of steganography techniques, which is used in generally used in digital media. You don't see it so much in the early linguistic techniques. And then I'm going to go on to do audio and image steganography, and then finally video coding. If I do my job successfully, hopefully by the end of the lecture at the very least, you'll be able to go away and actually know how to create 2 very basic audio and image steganography tools. So, and yes, the video steganography bit that I mentioned. Let's start with where it originates and what exactly it means. So steganography is quite simply, it's writing covert messages. So the idea is that you want to hide a message in something, but you don't want someone to know it's there. It's the words Greek in origin, coming from steganos and graphia, meaning covered or protected, and writing. But it doesn't actually appear. You don't actually see the words steganography appear in the literature until 1906, where 1906, 1606, if I can read properly, where it's published in this book. But that was actually written circa 1499. So it didn't actually get published for some time after. I'm not quite sure why. There are key differences between steganography and cryptography, which some people can they overlook because it has to do with what actually determines whether steganography is sort of like secure or not. So with cryptography, you're trying to protect something, you don't mind that someone knows it's protected. When you're doing, let's say, a bank transfer and that's encrypted, you don't mind that someone knows that you're exchanging encrypted information. So long as they can't read it, that's all you care about. Whereas with steganography, you want it to be covert. You don't want someone to know it's there. Because if I'm trying to hand over a secret message to someone, the whole point of that is it's secret. No one else knows it's there. So if they can detect it, it doesn't matter if they can't understand what's there. Just by them knowing that it's there means that steganography is essentially broken. So there are aspects of any security type topic, such as steganography, cryptography, that overlap. And one way in which it overlaps is this person's principle here. How did we agree that we said this? Kirchhoff? Yeah, Kirchhoff. So his principle is originally from cryptography, and it says that for a crypto system, it should always be secure, even if everything is known about it except the keys. So if you know exactly how a cipher works and its weaknesses, but you don't know the keys, it should still be secure. And you can say that that's true to steganography. If you've got something that's hidden with a particular algorithm, then in an ideal world it should be secure, unless obviously you don't know, if you don't know the steganographic key, you shouldn't be able to find it. So, the earliest mention of steganography in terms of actual practical application is told by Herodotus, who gives a story of how his master basically tattooed a message on the scalp of another slave and sent that message to warn of this revolt. So what he did is he took the slave, shaved his head, tattooed a message, waited for the hair to grow back, and then sent him on his way. So I think it just shows somehow that times have changed and that's not really considered practical anymore, or probably ethical either. So there were also some other quite early uses of steganography as well. So the principle of using a wax tablet was quite common. So what you do is you take the tablet, scrape off the wax, scratch your message in the back of it, and then cover it with a fresh layer of wax, and then you could carry that without anyone suspecting a message. And if they wanted to search it or what have you, they'd look at the tablet, they'd be able to see things which you'd write on it normally, but unless they were to scratch off the wax, they wouldn't notice that there's a message scratched into the back of tablets. And then there's this Aeneas, however you say his name, the tactician. So he's documented quite a lot of techniques, very primitive techniques for hiding messages. I mean, the two ones I've mentioned there are women's earrings, so hiding messages in women's earrings, but also, I can't quite remember how he does it, but he sends messages secretly by using pigeons. He does document some other sort of like more obvious techniques. So for linguistic steganography, which is typically text, he documents how you can basically encode messages in text by putting either dots above certain letters to indicate that basically you should take note of those letters, or by changing the height of strokes when you're writing the letters. These are some of the more sort of like prominent examples of linguistic steganography. So some of them use these types of techniques. The first one is quite a good example because it's out of everything that I've read, it's one of the examples that embeds quite a large amount of information for what it is. So this person embeds in an acrostic poem 1,500 or so letters, which is quite impressive. But I think the one that I like the most out of this is the technique proposed by Francis Bacon, and what he suggested is basically a precursor to what we'll soon see as least significant bit manipulation. So he said that you could hide a message by either writing using a normal or italic typeface, and this actually works surprisingly well because at the time when he was when this was being sort of like used and proposed, there was inconsistencies between people's handwriting and typefaces, and it was very inconspicuous, and it was a very good technique to use. Now, this photographic technique by Brewster, you probably have heard of it, but you haven't heard of it when it relates to him. So what he proposed is basically almost like a macro photography approach, where you could take a picture of a page or some text or an image, and you could shrink it down really, really small. It's basically the precursor to a microdot that the Germans used. But when the Germans adopted the technique and they actually used it, they were able to shrink often several pages worth of text and images down into a single microdot, and these could be embedded. In things like stamps, or they'll split apart the fibers of a postcard and actually hide the dots inside those fibers. Another technique that sort of like comes from sort of like the World War eras is this example. Now, I can't actually identify an original source for this. Everyone seems to sort of like reference each other when they say where they found this example. So it's one of those things that you can presume is probably true, but there's no. I haven't at least been able to find an original origin. Here's the telegram it was taken from. But during World War II, telegrams would be censored. So they wouldn't want, let's say, messages from the front line going home, or vice versa. They wouldn't want sensitive information being sent. I've just realised I'm talking about something completely different and looking at the wrong slide. So we'll see how that's used later on. But in this context, a spy basically sent this message, and it looks quite inconspicuous. To me, it doesn't make complete sense. But if you look at the second letter of that message, you should hopefully start to see something forming. And what's actually embedded in it is this message here, giving the sailing date of a ship. So that's very simple, by just taking the second letter of each word and stringing them together. So this is what's known as a null cipher. This method of sort of, well, you just take X character of each word or something like that, very sort of like nondescript. There's no sort of like specific indicator. That's what you call a null cipher. Right. So other types of linguistic steganography are invisible links. So you can use things like milk, vinegar, diluted honey, and sugar solution to basically write a hidden message on paper, and it's completely invisible to the eye normally. The way that you reveal these messages is by heating the message over a flame, over a candle or something, and then these solutions, which are normally clear to the naked eye, then become readable. There is also this technique. This is a modern technique of basically shifting the spacing between lines by a 300th of an inch, and the 300th of an inch relates specifically to printers. So some of you might be aware that printers generally print at 300 dots per inch. So this proposed technique says if you've got a document of text, you just modify the height at which lines are printed. And it's quite a good technique because it demonstrates robustness. You can actually photocopy pages of text, and the method of embedding is actually preserved completely. Okay, so watermarking is another sort of like, it's a different application for steganography, or at least the kind of techniques that are used in steganography. You're trying to just hide information for sending a covert message. With watermarking, you're trying to embed information, and you don't mind that people know it's there or that it's particularly easy to detect. What you're trying to do is you're trying to embed information, supplementary information, but you also want it to be difficult to remove. And this is commonly used for when you buy things like MP3s online and what have you. They often have the information about the seller and the buyer encoded in them, and it's one of those things that sort of like helps to trace where things come from, and apparently to prevent piracy. I'm not sure quite how widely it's used, but the important thing is it's very difficult, and you'll see why when we discuss some of the techniques, why it's so difficult to actually remove what's embedded. But another important factor, whether it's watermarking or steganography, is if you're modifying something to embed a message, you don't want it to be noticeable that it's there. For instance, if in the very first example they tattooed the message on the scalp of the slave and then just sent the slave before his hair grew back, completely pointless. but you don't want to have anything that's sort of like noticeable, ideally to any degree, whether it's blindingly obvious or somewhat subtle. So another type of arguably linguistic steganography is printer steganography. Who here has a printer that is any of these makes and uses it? By a show of hands. Well, you might be intrigued by what I'm about to tell you. And for all of these printers, there have been known to be basically steganographic techniques applied to the documents that are printed to encode the serial number, at the very least, the serial number of the printer and the timestamp for which the document was printed. Others go further to probably include sort of like more specific make and model, but I suppose you can get that generally from the serial number. So they do this by printing dots, and it's generally sort of like something like yellow dots, and they're very, very small. So obviously it's designed that you won't really notice it, and generally you don't. They only appear under a magnifying glass or under some level of magnification. They're not easily noticeable. And quite interestingly, whilst all these printers have been known to use this technique, the methods in which they use to encode they've never been decoded. Very few have. So no one actually really knows the scheme that they use or what have you. But according to sources, this was introduced so that manufacturers of printers could reassure governments that their printers wouldn't be used for forgery, because obviously it gave some level of traceability to the documents that were produced. Right, so steganalysis is the counterpart to steganography. It's the process of being able to detect whether a message is encoded or not. But again, it's one of those things, like I said with the security, you don't need to know what the message says. You just need to detect the presence of it. So there are different approaches that you can use this. You can use targeted and you can use blind steganography. With targeted steganography, you know the way in which it's encoded. You know, like the algorithm or some factor like that. So you're doing a specific steganalysis approach based on what you know. Whereas with blind steganalysis, you don't necessarily know either the technique that's used or whether information is hidden at all. So that's slightly more complicated for obvious reasons. And the problem of steganalysis is often explained through this principle of Alice, Bob, and a warden, and who might buck the trend. So this prisoner's problem, which you might have heard of before, at least the concept of sort of like Alice, Bob, and an eavesdropper from things like if you've done, let's say, RSA, for instance. Well, it's quite an old method of explaining it, and you can find this is the original use of it, I believe. So if Alice wants to send a message to Bob, what you really don't want to happen, or what you've got to be mindful of, is that your warden can try and intercept this message, and they can do any manner of things. And as we see, there are different types of wardens, and they all sort of like can do different things to the message, and as a result, different things can happen for the recipient. So a passive warden is the simplest in a way, and it is the most subtle one, because all it does is it observes basically information which is exchanged and tries to derive meaning from it. So if two people were exchanging a message and I was a warden, I would just look at that information, maybe make a copy of it or whatever, and then try and sort of like work out what they're saying. But I wouldn't actually modify it. So you don't really have any proof or knowledge as a sender and recipient that your message is necessarily being intercepted. Active wardens and malicious wardens aren't quite as subtle. So with an active warden, when you're trying to not only determine the presence, but you're also trying to prevent the exchange of secret information. So to an extent, you will change the message. But a malicious warden will take this to an entirely different level, and it can try and impersonate parties, fabricate messages, significantly change it. The idea here is to catch people communicating or just disrupt and stop them from being able to communicate at all. I've got here, so this is the Telegram thing that I started to explain earlier, and then realised I was thinking of the wrong thing. So when telegrams were sent in the war, they were censored because they didn't want secret information or overtly written information to get through. So what they would do is they would either, let's say, block out with a marker pen blocks of text if it was, if people were trying to say stuff they shouldn't. But what they also did is they also changed the way things were phrased so that hidden stuff couldn't get through. And this is an example of what was essentially it's an active warden technique. So in the original telegram they had father is dead, and they changed that to father is deceased. So when the recipient of that telegram got father is deceased, it prompted them to reply, is father dead or deceased? Now, as I was saying earlier, there doesn't seem to be an original source for this, or at least not one that I've been able to find. So you don't really know sort of like how true it is on that nature, but I think we can safely assume that it is probably true. And that's quite interesting because it doesn't necessarily say, right, there's something secret hidden in here. But what you can definitely say is there's obviously a difference in meaning between dead and deceased, or at least something further than what those words would mean in a normal context for any normal person communicating. They've got some additional level of sort of like semantics, if you will, that they've put into those two words. So that's all sort of like this is where steganography started, where it came from, the primitive techniques. Here I'm going to get into the more interesting stuff, which is basically the techniques which is used for digital media. So injection and sort of substitution and transform domains are probably the most common techniques used. You do see generation and streaming and real-time techniques being used as well. Generation there's not a lot of that, and you'll soon see why when you realise exactly how that works. There's not a lot of stuff out there that actually uses a generation technique. And streaming in real time can present problems because you're doing it in real time, and when you understand how things like that have to be represented, you might also start to see why that's sort of like the less common choice. So, injection is, I would argue, is probably the simplest digital steganography technique. So what you're doing is you're inserting portions of information into a video file, and files which you can do this with really quite easily are exe files and WAV files. And the reason you can do this is because exe files have an end of file marker. So once they hit that marker, they're not interested in anything else that comes after it, if anything else comes after it. This technique, as well as, whilst you can use it to exchange messages covertly, it's also the same kind of principle that's used by like self-extracting executables. So they embed basically their compressed payload after the end of file marker. WAV files, the same kind of concepts, just handled slightly differently. They don't have an end of file marker, but what they do have is they've got a fixed header, and within that fixed header they say my data portion of this file only comprises X number of bytes. So what you would assume is that a media player will look at that value and it will only read that number of bytes. I mean, depending on how the media player is implemented, technically it could just keep reading till the end of the file, but it should really read from the header. So you can actually use that to basically just append information to the end of a WAV file. So that's something quite simple that you could do with a very simple program. But these techniques they're not very secure because you're taking a file and you're just adding stuff to it. It's a bit like if you were to give me a printed document and I was to write on it on pen. It's quite clear what I've added. You can quite clearly see a difference because you're adding information which basically shouldn't be there as well. It's not like you're changing information that was there. Changing information that was there is substitution. So this is where you're modifying pre-existing data of the file, and with this technique, you don't generally change the file size. I mean, when we get to video, you might see how there will be fluctuation in the file size, but there's nothing in what you're doing that should really change the file size. But you've got the disadvantage with this kind of technique that your steganographic capacity is limited. With the other injection technique, you can add any amount of data to the file that you want. There's no limit on it. Whereas with with substitution, the steganographic capacity is limited by the amount of information that's already there. So the most common form of hiding information by substitution is by using sort of like either least significant bit or some other kind of bit mask. So least significant bit is the simplest, and what you're trying to do is if this is the this is the character that we want to encode, and this is some data. All you're going to end up doing is you take a bit in turn, and you embed one bit of the message that you want to embed in a byte. So in this case, you've got 1 here. The least significant bit here is 0. So after the embedding process, that becomes 1. And you just keep going like this. So for the next one, you've got 1 and you've got 1. So that's not going to change. So that stays as 1. And here you're trying to encode 0 over 1. As I'm explaining it, you can see that what goes before it, the rest of the binary data, it doesn't matter. But also, if you think about this in terms of binary, because I'm modifying the least significant bits, I'm just changing the value of this number here by 1. So the difference is hopefully subtle. It obviously depends on what data you're encoding in. But if you were to just take a standard byte, you're just changing. You're basically sometimes adding a 1, sometimes you're not. Well, sometimes you're just subtracting. So that's how that kind of technique works. And we'll see later on how you can apply this to both image and audio steganography in the tools I'm going to hopefully show you how to produce. So generation techniques I'm not really fond of personally, because I think I believe them to be quite limited, and the amount of information on them is also limited, and I believe those reasons kind of overlap. So with a generation technique, you're generating a container file based on your data. So you don't have something which you're trying to embed into. You're saying, this is what I want to send. I need something to contain it, and you produce that something. But that does have an advantage because there's no original container. If you take the examples that we've had previously, if you know the original source, so let's say for instance that you're going to use either LSB substitution or injection to basically modify a WAV file. If you've got the original WAV file and you've got the modified one, you can quite easily compare them, and you can spot differences. And that's quite a problem if it ends up that your original container happens to leave your secure domain, as they call it. But in this instance, there's nothing original to compare it to. You don't have the non-modified version of your container because you're producing your container. So the main problems with this, which I don't like, is that the thing that you're generating has to be relevant to those who are communicating to make it plausible. For instance, if you've got two people who sort of like are car enthusiasts, then it makes sense and it's not suspicious for them to maybe send emails with pictures of cars attached and for them to have some kind of discussion about that. And those images of cars could be completely generated, and those could hide information. So if it's something like a road and you've got cars on it, the position of the cars could actually encode a message or something along those lines. So you've obviously got the problem that it's not a very practical technique in the sense that what might be plausible for me isn't going to be plausible for someone else. And from what I've been able to gauge, I haven't actually tried to produce this, but from what everyone else says, and presumably from the lack of published work on this, it's very time-consuming and complex to produce this kind of stuff. Especially if you're trying to just generate something that seems realistic based on any form of input. Transform domain techniques are very popular in particular for image steganography with JPEGs. You also see the discrete cosine transform cropping up in video steganography, which we'll see later. But this is quite complicated the way it works, and I'm going to give a very basic run through of how it does work, but it's not going to go hopefully too in depth. But I'll end up getting to that later when we discuss the image steganography stuff. But first of all, audio steganography. So this is where I'm first going to introduce you to the concept of lossy and lossless compression, and this is really quite important because it affects how easy or difficult it is to embed information in a container. So with audio steganography, generally when you're trying to hide information in an audio file, you're modifying the bytes that make up a sample. And there's different ways in which you can do that, and the way in which you do that doesn't really matter, but that's essentially what you're doing is you're just modifying the sample. But something to be mindful of is you've got uncompressed formats, which are things like WAV, BWF, and so on. But you've also got compressed formats, and these form these two groups, lossy and lossless. Naturally, uncompressed formats are the easiest to embed into because you don't have to think about stuff. And also, lossless techniques are also lossless file formats are also easy to encode into, but you still have the notion of compression. Compression still happening. You still have to be sort of like embedding and extracting at the right point. But lossy compression is a lot more. It's a completely different game. So when you're doing lossy compression, and this is what's used in video and JPEG and things like that, you're taking something original, and when you save it, you're storing it as something different. But in storing it as something different, there's an irreversible process that happens along the way. And because that process is irreversible, it means that when you're trying to basically display the image or what have you, the next thing that you're producing, you're not producing the exact article that you started with. What you end up producing is purely an approximation. So, this is a description of basically the header of a WAV file. And it might look a bit intimidating, but to be honest, there's not a lot happening here that you need to be aware of. Quite a few of these things are constants. So where you've got, let's say, RIF, FMT, and so on, and data, these are just basically constant portions. But a WAV file it's got a 44-byte fixed header, and so the only thing that you really need to be concerned about is this thing here, your bits per sample. By using that information, or just by extracting that information, you've now got everything that you need to actually be able to embed data, because you know that your data starts after here. And this is where you define your size, as I mentioned. So I said earlier that WAV files have a size in their header, and this is done by a 4-byte integer. So if you were to read this file, you knew the size of the limit of your data. If you're doing a substitution technique, you need to know how much your data is, but also how many bits per sample. So with that information of how many bits per sample you've got, you could then do LSB manipulation and embed the data in the least significant bit of each sample. So what I've got for you here is a couple of clips of audio. This is just using the same sort of like generic music that I had during that introduction video. And I'm going to show you two examples first of all, and I'm going to point them out to you. So I've obviously got the original sample, which I'll play for you. I'm only going to play about the first 10-15 seconds of the sample because of the audio file, but that's all that's relevant. The rest of it, there's no data hidden in it. But for when we get down to maybe some of these, but for the original one, there's nothing hidden in it. That's just the original audio file. This one here, what I'm doing is I am embedding data, but I'm doing it in such a way that of that data portion, I'm changing the least significant bit of every single byte. And you should hopefully be able to hear the difference. It is quite pronounced. And then I'm going to play you 3 clips. And I just want to know, it's another one of those things where sort of like I'm going to ask you if you'd be so kind as to sort of like indicate on your questionnaire which one you think has data encoded in it. And then at the end, hopefully, I'll be able to tell you what the results are. I can't actually remember this, so I can't influence you in any way, so I have to wait until the slide tells me what's what. So, with that in mind, I will play you the original sample, hopefully, and then... oh, blimey. Well, this is annoying. For anyone who hasn't used PowerPoint in a Mac and is thinking of doing it, don't. Right, this is how we're going to do it. So that's the original sample. And hopefully you can spot the difference. So you've got that really sort of like, you've got a really horrible hiss overlaid. Now, what I'm going to do is I'm going to play you the other three samples, A, B, and C. And I want you to hopefully, if you can, I'll play the first 10 seconds again. And just have a think and see if you can detect if there's anything hidden in them. And if you don't think there's anything hidden in any of them, which could also be the case, I could be checking to see if this is some kind of placebo effect, indicate so. Because I believe I did give you a none option. Right, so as a show of hands, who thinks there was nothing encoded in any of them? Who thinks it was A? B? C? Well, I kind of tricked you. They all had stuff embedded in them. So, I can't quite... let me work out which order it was. So, the first one I showed you had data embedded at half of the sample. So instead of embedding at the least significant bit of the sample, well, I was embedding halfway through the sample and in the least significant bit. And I think, well, when I was preparing this, I thought there's no obvious difference. I can't tell the difference between the original or the one that I'd modified. The next one had a quarter, so I was modifying 4 bits at equal points throughout the sample. Now, it's worth noting that the position of the bits could indicate more significant or less significant parts of the sample, like more noticeable or less noticeable frequencies. So that one for each sample I was modifying 4 bits, and then the last one was just the normal LSB encoding. But hopefully you'll find that well, you might be interested to play about with that and see exactly at which point you start to get something noticeable. And I'll give you a quick run through of how it's possible to produce a tool that can do this in Java in probably about approximately, including the encoding and decoding process, it probably takes not much over 100 lines of code. It's really quite simple. You might even be able to do it in less than that, in less than what I've done. And I think, if I remember my slides correctly, and my pointer decides to work, that's coming up. So all you really need to be able to do this, if you want to implement it in Java, you can implement it in any language that you like. It can be Java, it can be C, or whatever you want. Because all you're doing is you don't have to, because it's an uncompressed format, you don't have to worry about the types of compression, because there is none. You're just modifying the raw data. So by using Java I/O, all you want to do is you just want to be able to modify the file at a byte level, and then manipulate those bytes by using bit operators. So if you were to use, and I will hopefully be able to make these slides available after the lecture, but if you were to refer back to the one where I gave you the information about the WAV file header, by reading in the bits per sample from the header, and then dividing that through by 8 to give you the number of bytes that comprise a sample, you can then start to encode data in the data portion of your file. So basically everything after the first 44 bytes. And you could do that by using, let's say, you could do it just by using LSB of the sample, or you could do things like I did there, where I was changing other portions of the audio file. And at the beginning of the lecture and on the handouts, I've got the website address for the website that I've set up, kind of for my project. It mainly documents sort of like the work as I've gone along. There's a blog on there which is basically me complaining about why things don't work and how I can't answer questions on why I've got these problems. But what I've also got is I've also got a couple of tools which should allow you to experiment with this stuff. And this just runs when you upload something here. It's just running it's just running Java code. I'm not pulling wool over your eyes and doing extremely clever stuff behind the scenes. It's literally, you follow this guide, you'll have the same jar that does this essentially. So you can, if you want, you can upload a file. I think it's limited to 2 megs, and it can encode or decode it, and it'll produce you files accordingly that you can download. What I have added is I've added the ability to basically encrypt your data, and that will encrypt it with AES. And you'll see the reasons why I've kind of like added this as an additional thing. It's not something that you have to do. But when I get onto some of the steg analysis stuff in the image steganography section, you'll see sort of like what advantages it can have. And I think what I will do before starting the next section, which is a bit lengthy, is I'll allow you now to have a break now, as we're now sort of like 45 minutes through. So I'm going to cover very, very quickly, hopefully, the way JPEG images work. And this also explains how TV signals are represented, how PAL video signals are represented, how most things are. It doesn't apply to NTSC video formats for some reason. They want to be unconventional. But the key part of it is this transformation from RGB into this other color space, which I'll get to in a minute. So these are basically a summary of the steps that are involved in being able to produce a JPEG image. So what you can do is you can actually exploit the discrete cosine transform, the values it gives you, after the quantization process to be able to embed stuff, and I'll show you kind of how that works. But before we get started on that, I'm just going to hopefully quite briefly explain what this is. So RGB is quite... it's a color space which can represent a lot of information. But the problem is if you... to bear in mind when you use JPEG images are usually used by cameras. They're not you don't usually use them when you're producing computerized graphics. You'll usually use a different file format for doing that. But they discard information which isn't relevant to the human visual system. So the eyes can only perceive certain things and certain things well. So you're more sensitive to the luminance of an image. So your eyes are more likely they'll pick up bright changes in brightness better than they will in different things, in other different components like hue and saturation, which are represented by C subscript B and C subscript R, which I'll just refer to as the difference in blue and the difference in red, respectively, and you'll see how why I say that. So this luma component, Y prime, it relates to the luminance of, or so basically the intensity or the brightness of a pixel, and you've then got these two, difference blue, difference red, which are they're essentially chrominance components. And they're a scalar difference from Y prime. So you would compute the difference in blue by working out the difference between Y prime and pure blue. Same kind of principle with the difference red. So this is quite the ugly way and the quite honest way of how to do it. So you can use a standard matrix transformation to basically convert an RGB color space into this color space. So you don't really need to understand how or why that happens. But the important thing to realise is that this component here that's the more important aspect to it. These differences here, they're sort of like they're less noticeable, and this is where you get your chroma. This is where you get downsampling and chroma subsampling come in. So if in an RGB color space, in a standard red, green, blue color space, you've got all this information that you've got, and you don't need it, then why not eliminate the stuff that you don't need? And this is where you get downsampling, because you're changing the way that you're representing colours by switching to this different colour space. You can easily discard information which is less noticeable to the eye, and that's essentially what JPEGs do. They discard stuff of higher frequency, which the eyes can't easily detect or pick up on changes to. So the first one, and these are expressed as ratios. So 444 is you've got no downsampling occurs. You've got full color resolution. So what you've got here is you've got the difference in red and difference in B values, and this is your luminance. So I've kind of tried to illustrate this as kind of like a grayscale ranging from white to black, kind of like how you'd have a opacity ranging. I should also say these graphics are purely to sort of like illustrate the concept. They're not technically accurate. They are just purely as a demonstration piece. So if you have a look here, in having no downsampling, you essentially get the same types of colours coming through. But when you start to reduce and narrow down how many samples you're taking, and do things like 422 and 420, the number of colours and the changes in them are less. So here, what you're doing is you're doing half the horizontal, but you're keeping your full vertical resolution. So if you reference this original, what you're doing is you've got the full vertical, but you've got those two sets of colours there and there. You've got the direct correspondence there. But you've also got the green and the yellow, and the green and the yellow. So what you're doing is you're sampling there, but you're only half sampling in your horizontal. So you're discarding the next set, but then you're going on to that set and discarding that set. And it gives you this other representation. You're discarding half your horizontal resolution because, well, you don't really need it. There are other methods, such as 420, where you're halving your horizontal and you're halving your vertical. So if you have a look here, all you've got is that component and that component. You've got essentially no vertical component really. You've only got sort of like a unit of one, if you will, and you've got the half sampling that you see here. So that's a way that you can sort of like sample and reduce the colours which represent an image. And this is the lossy part, or one of the lossy parts of JPEG compression, because once you do this, you can't get back to what you had before. You can't get back to the original color representation you had. So that's why when you save an image as a JPEG, it's not going to be the same when you display it as what you originally had. But this works well for natural photographs, because in natural images of things in the real world, you don't have sort of like amazingly crisply defined edges and things like that, and your transitions of colours are generally quite smooth. You don't have sharply occurring colours. So by reducing your sample, you're not really actually hindering yourself in terms of what you're presenting as something to display. And yes, so that's that. And now you've got block splitting. So I'm going to explain this very briefly, and it relates to what we'll soon see as macro blocks in videos. So you divide your image up into small sort of like subsections, and depending on the method that you use, depends on the size, basically the size of these individual blocks that you break your image down into. And then what you're doing is you're then for each of these blocks, you're computing a discrete. You're transforming it from a spatial domain into the frequency domain, which is what the discrete cosine transform does. It takes something from spatial, so the visual representation with an x and y component, into a frequency domain. But before you have to do that, you have to adjust the ranges of the values. So you take it from. So these values will range from 0 to 255, as they would in, let's say, like an RGB or a CMYK color space, into something which is zero-centered. And the only reason you need to do that is just basically for the transform, for the purpose of the transform. So you get a new range which centers around 0 as opposed to 127. So this is how you don't really need to understand this. added it as sort of like additional information if you want to. But this is how you compute your discrete cosine transform, and you compute that for basically every single block. And what that'll eventually give you is it'll give you a matrix of discrete cosine transform coefficients. And those coefficients are the important thing. So what you then do is you then take those coefficients and they're subject to what's known as a quantization process before having entropy coding applied to them. So as I mentioned before, they're not very sensitive to changes in high frequency brightness. So when you're doing your quantization, you can disregard those because no one's going to notice the difference. No one's going to notice if they're not there. It's a bit like, you've probably heard this one before. It's a bit like WAV and MP3. If it's something that's going to be listened to by a person, the human can only hear frequencies between certain limits. So you don't need to encode code frequencies outside of a range which you can't hear, which is what formats like MP3 exploit. So when you've got those values, you apply a quantization process, and all quantization is that you're taking a set of values from one range and you're reducing them to a smaller range. Again, this is quantization is an irreversible process. It's only this and the downsampling or the chroma subsampling, whichever you want to call it. Those are the only two sort of like lossy aspects because you can't undo them. So that is So as you're quantizing it, you're dividing through by a constant, and then you're rounding. That's it. In basic terms, that's how the quantization process works for DCT. But that rounding is something which you can't undo. So then you encode those blocks, and this is true for this method of this zigzag method of encoding is the same for image as it is for video. So what you're doing, the reason you're doing this zigzag type pattern is that in following that pattern, you're encoding things of similar frequencies next to each other, and it's purely for sort of like the way that you encode this, and you can apply different types of compression techniques. And obviously, if the data's in a particular format, it can be somewhat helpful to use that zigzag type pattern. So, in terms of image steganography, you could, if you wanted to, do the JPEG stuff, work with a discrete cosine transform, and modify the least significant bits of the coefficients that you get from applying the transform. But obviously, you'd want to do that after your quantization process. You could do that, but it's not easy, really. Or you could use a lossless compression technique by modifying palette-based images. So with a PNG, you've got there are basically two different versions. You can have a 24-bit palette or a 32-bit palette. 24-bit palette, you're just encoding red, green, and blue. In the 32-bit version, you've got your red, green, and blue, but you've also got an alpha transparency. So all that really means is, in one format to encode a pixel, you use 3 bytes, and in another format to encode a pixel, you use 4 bytes. Or you could use a GIF, but I think this is more limited because in a GIF you've only got 256 colours because your palette is limited to that. So the way you do image steganography with a GIF is that you just change the values that occur in your palette. So an approach which I experimented with was basically LSB manipulation of the colour values for a PNG image. So you've got these two different approaches. I only used this simpler 24-bit approach, though, as you can see, there's no transparent background to these graphics. And there may be information embedded in some of these, none of these, all of these. If you could be so kind, could you just have a think and indicate so on your paper, and I'll just give you a couple of seconds to think about which is which and to compare the difference. I should point out these answers that I'm collecting are purely they're just for my own, just to see how successful these techniques are at embedding stuff. It's not a case of you're getting it right or you're getting it wrong. If you think there's stuff embedded there, if you think you can see a difference, please just tell me and be honest about it. also something that I should have pointed out is that these are completely anonymous. I don't really care who thinks what about it. I'm just trying to work out what people are perceiving. So, is that long enough? Everyone looked at them? So that's the truth about it. These two on the left, there's nothing embedded in them. That's the original image. And this one on the right is the modified version. But can you actually see a difference? Open question. Yes? No? Hands up for yes. One person. Brilliant. Hands up for no. Okay, that's good. So what I'm actually doing is, and you can see this, if you were to open these two images in something like Photoshop and whatever, and you were to use an eyedropper tool, you'll actually be able to see, if you were to start in the very left corner of both images and work in that direction, horizontally right, you'd be able to notice that the RGB values, they actually differ, and they can differ by, by like 1 or so. So you can actually see how I'm changing the LSB and actually causing the colours to fluctuate. So yet again, this is possible to do in Java, and I've produced an online tool that can do this. You can upload stuff up to 2 megs, and it'll produce, let's say, the image with the message hidden in it, or it'll extract the image. And I've also added the additional stuff for encryption, but that's not really something that you need to concern yourself with. But you'll see later on why I've done that. And this image is actually taken from the homepage of my website. So it used to be that. It used to be an image that didn't have anything in it. But then I changed it to that, and that's been there since, well, not quite day one, but close enough. So it's been there since the early days of September. And there is a message embedded in that. There is no password set, I believe. So if you are interested, download it, run it through that tool. You might find something hidden there. I'll leave you to work out what that is. So this is how you do it in Java. It's a bit more complex than the audio technique, because you're having to basically cast things and getting the data that you need to encode is a little bit more long-winded, but it really isn't difficult. And again, you can do this sample in implement this technique in Java, following those steps, in probably, I'd say, about roughly 150 lines of code for both the encoder and the decoder. You might be able to do it in less. I was doing this purely as sort of like preliminary research. It wasn't sort of like, let's try and get the best method of doing this. So if you've got a better method, I'd also be interested to hear it. But what you do is you read your image into a buffered image object, and you compute basically the raster version. So from this rastered version, you can get a data buffer. So what you need to do is you need to cast this data buffer object to a data buffer byte, and then from there there's a get data. There's a get data method which will allow you to get an array of basically all of the pixel values, the RGB values for the entire image. And then by manipulating that byte array, and it's probably the way I did it, and probably the better way to do it, is you produce a separate output byte array, which is obviously the same dimensions, and you just manipulate the bytes and you store ones in your array. And then just by using image IO, there's a write method which will just allow you to write that byte array out to a PNG file. It's quite simple. It is that simple. This is the only sort of like, that's as complicated as it gets, and that isn't really that. If you look at the API documentation for Java, it's quite straightforward. So if you want, have a play with that, and you should hopefully, by following those steps, be able to produce something that's capable of encoding. So these two graphs are computed from those images that I showed you, and this gets onto why I've encrypted stuff. So as you can see, and on the original one, notice I'm plotting the frequency against the ASCII value, and here the frequency against the ASCII value. But if you have a look here, your frequency is up to 450, whereas the frequency here doesn't go higher than 90. But there's also, look at the general profile. So there's no really distinguishable pattern there to it. Whereas here, you've got this quite interesting spike. Does anyone know what that spike is? At a guess.
Encrypted data? No, it will be hidden data.
Yeah, but why do you think you know why it spikes around those values? Look at the numbers.
Are those they're the ASCII values, aren't they, for like AB?
Yeah.
Like
So yeah, that's it. So they're the ASCII values for normal text. So by looking at this, there's a few so these graphs are. I've taken basically the LSB of each byte where you could have embedded stuff, and I've just put it together in a string and looked at what that string says. So here you get what is essentially you get garbage. There's quite an even and random distribution of stuff. Whereas here you're getting a very prominent spiking where you've got normal ASCII alphabetical text embedded, and that's what's embedded in that image. There's another spike here which is around, I think it's 32, which would be the space character on the keyboard. And for some reason I think sometimes you get a space at the I think it's at the null character sometimes, but I think that's generally just due to the formatting of the image and characters which are needed to produce the image. So by not encrypting data, you can see trends and you can see patterns. It's just like if you were to produce a computer with a random bit of data and text. It's quite easy to produce something that can distinguish between texts to an extent. What's text and what's just random garbage. So this is what happens if you encrypt the data. That easy characteristic to follow disappears, and you get more a distribution which better matches that. You're not going up to ridiculously high numbers of frequency. And I'll get into when I explain AES, which there's only 2 slides on it. I've kept it quite simple, but you'll see kind of how and why that works. So video coding. This is where the fun stuff starts, or stuff that's actually quite difficult. But hopefully, I'll try and explain it as easily as I can. So with a video, you have like a container, and a container can contain different streams. And what you're probably used to when you're watching a video, the concept of having an audio stream and a video stream. But you can also have other things, like you can have other data streams, and these can be used to add things like subtitles and additional information. So this does open you up to as much as you could sort of like embed things in that to the video or the audio stream. In theory, you could just maybe add. I haven't tried this, and I haven't really found anyone anywhere that's tried to do it, but I haven't been looking. I can't see why you couldn't just add a data stream, mark it as being a data stream, and then just hide a message in your video that way. However, let's consider a frame of video. So notice that I've put the frame number down here. So and I'm going to hopefully show you. So you've got frame 1, which looks like this, and then you've got frame 25, which looks like this. Not a lot different is happening here. Now, bear in mind that video files are they're generally sort of like 24, 25 frames per second, or about 30 frames a second, usually. So what you're actually witnessing here is you're witnessing what is a second's difference in what's being recorded as a video. So I'm going to point out to you that right hand. Have a look at it. That's frame 1. That's frame 25. Do that one more time. Frame 1, frame 25. There's a slight movement of the fingers. Could you see that? Was that clear? Oh, it seems so. So if you think about it, in that frame you've got a lot of redundant information. That's the only thing that's changing. So when I was extracting this frame from a video, admittedly I was extracting it as a PNG, which isn't really very well compressed, but that's a 2 meg image, right? The other frame, frame 1, is also a 2 meg image. So if you were to encode every single frame, and I can assure you that in your average 1 minute video, you'll probably have about 2,500 frames. That's going to get huge. So the way you get around that is that you don't need to encode everything as a literal image. And we'll see how that works. And the way that videos deal with this is they split it up into these things called macro blocks. And this relates to the block sampling and the splitting up into blocks that you see for JPEG. So what you can do is you can discard everything apart from that. You don't need to say, well, this block here is exactly the same as the block that you saw in the previous frame or the frame before that, and so on. All you need to say is you just need to describe that change. And that's done by using different frame types. So an intraframe, these are in short referred to as I-frames, P-frames, or B-frames for simplicity. But an intraframe is basically, it's the full representation of a frame. So it uses what is essentially JPEG techniques to represent the image. And then you've got what are, these are two different types of predicted frames. So a P-frame is predicted based on a frame that goes before it, and a B-frame is predicted based on frames either side of it. And you'll see how the size of these representations varies as per this illustration. So again, this is just sort of like really to illustrate the concept. The height of these things isn't, there's no technical accuracy there. But the thing to note is that, so I'm using red for I-frames, purple for P-frames, and blue for B-frames. So you get this group of pictures. It seems to usually be about 12 frames. It seems to be the accepted default, but to be honest, it can be anything that you want. So you encode an I-frame, and then you've got a group of P-frames, which are predicted from a frame or frames that go before it. And then you've got these B-frames, which can be predicted of frames either side of it. And they're usually predicted by one of either side. But notice the height at which I've drawn these, and that kind of corresponds to how much information is needed to represent them. So here, you need a lot of information, but for the P and B frames, you don't need a lot of information. And for the B frames, you need even less information. Because what you're doing is when you've got these frames, these groups of P frames and B frames, they're just deltas. You're just describing changes. You're saying, well, in this frame, that block moves there. And when you've got something moving from, let's say, here to here, between two frames, you can generally say, well, that group of pixels moved there. You generally have that correlation. You don't. What you're displaying is the image doesn't change that much unless you've got a change in lighting, or you've got objects that just pop up in the scene. You can generally say, well, this group of stuff moves there. And this also explains why video coding is quite a computationally intensive process, because you're looking at a group of frames, you're taking a block, and you're searching outwards, and you're trying to say, right, what do I match with? Right, so this is what I've really sort of been really intensely working on for several months now. I've explained the image and audio techniques because I believe that understanding those helps you to understand the video techniques. There's information in the image and audio techniques that I've been able to use. So that's why I've kind of structured it like this. So I'm going to really start by sort of like explaining other techniques in the literature. And really, when it comes to video, there's not a lot of techniques out there. If you look at statistics, image and audio, software for it, there's loads of it. There's loads for image, there's some for audio. Apparently, according to one thing I read, there's 3% of the steganographic software on the market uses video. I've been able to find a handful. To be honest, a little over 3, so I don't think it's really quite 3%, but I don't know. Maybe I'm not looking in the right places. So, I said streaming and real-time, there's different techniques for that, and that's because of the way you've got to represent your information. But when you come to streaming and real-time, you've also got to think about how you're transmitting your data. So there's nothing to say like when you're transmitting a video that's a stream in real time, that you can't have some audio data, some video data, some audio data, because it's multiplexed. So you're just being presented with this information. Some of it is audio packets, some of it's video packets. If you were to have another stream like a data stream, some of it would be data. There's no reason why you couldn't have that. But in the same respect, there's no reason why you couldn't have all your audio frames and all your video frames. There's nothing about the file structure which is limiting you from doing that. Can you think of any reason why this would be completely undesirable? Anyone? Yes?
So all the data would end up together, the stuff that's meant to be hidden would all end up together in the same place.
Kind of. You're right on the same, along the lines of sort of like all the data's in the same place. Don't think about hiding stuff yet. Think about if you're watching a video online. What do you know from this about the data? What's going to be problematic? Can you think? You're so close. You're really quite close with what you're saying, but don't think about hiding. Yes? Yeah, that's essentially what you're going to get. So if you think about it, when you're watching a video online, it's got to buffer. and you're downloading bits and bits at a time. But if you're structuring your file like this, you've got all this audio data and then all of your videos at the end. So you're going to basically have to wait for over half of it to buffer before you can actually start playing it back to the person, but there's no video. You've got your audio, but you haven't got your video component. So what things like, whether it be YouTube, iPlayer, or whatever, when they're encoding a video, this is what they're aiming for. They're aiming to sort of like heavily multiplex the different streams so that when you've downloaded something, that's, even if it's a small chunk, that's a chunk that you can use. So by heavily multiplexing that, it helps to alleviate the problem of buffering. So you're not waiting for a huge chunk to buffer before you can play it. You can hopefully wait for a small bit and play it, and then hopefully, depending on your connection speed. And this, you'll be able to play it back properly. And this is particularly important if you're trying to stream stuff to mobile devices. Because if you're limited by, let's say, 3G or 4G or whatever, your bandwidth is quite small. So the issue of buffering becomes more of a problem. You usually have to, if you watch stuff on your phone, you usually have to wait longer for it to buffer. So that's an important thing to consider. And in this paper, these people talk about hiding information in FLV. Now, FLV did used to be quite popularly used, and probably still is to an extent, for displaying video online. A lot of places like YouTube and iPlayer and what have you, they've switched to what you'll see in a minute, which is H.264. It allows you to do things like HD quality video. The compression on it is quite good. So you don't see it quite so often, but one thing that they did discover in their work was that FLV is a very, very, and for those of you who don't know, it's Flash video, basically. It's a very robust format, and you can just inject data into it, and it will continue to play back. So the way FLV works is that you have these sort of like these audio and data packets which are multiplexed together, but you just prefix video data with basically a video tag. You prefix audio data with an audio tag. And what they found is that you could just, after you'd encoded your section of, let's say, video data, and before you put a tag for the next set of data, you could just inject data, and lots of it. But what they also found, which is really quite interesting, is that you could remove quite a lot of these tags that marked the different portions, and it would still play back. So it's a very robust and very resilient way of not only being able to code data, but also, if you think about it, being able to hide data. Because not only can you just embed stuff, but you can also change stuff that's already there. Right, so MPEG is... sometimes it's kind of referred to as motion JPEG, in the sense that JPEG images, or at least a similar technique to it, is used to encode the iframes. So what this means is that you can hide stuff using the DCT coefficients. You can use LSB manipulation to change what's hidden in those coefficients, as I've discussed before, and this source discusses how exactly that's done. So that's one way in which you can use LSB manipulation. This is another source which discusses how you can use LSB manipulation to hide stuff in video. And this is quite a puzzling one, because it doesn't give a lot in terms of answers. So they say they can do this. They say that they can hide basically an image in a video, and it's a technique specific to hiding an image. They say it's implemented in MATLAB 7, but they don't give any mention of the video format or codec, which makes me think that maybe the method they're trying to use, because they're literally modifying pixel by pixel, is maybe they're using a lossless video codec, because I don't think that they'd be able to get the techniques. Because I tried this. I tried to modify pixel values in video, and I found it to be unsuccessful. Maybe I was doing it wrongly. I don't think I was. But I wasn't able to basically get those same pixels back because of the technique that's used, the lossy compression technique that's used for sort of like JPEG type images. So I'm a bit perplexed as to sort of how they've actually gone about doing that. But to say that I don't know how they've gone about doing that could be true for any of the video steganography techniques, because a lot of people will say, well, we did this, and this is on a high level how this works, but they don't actually tell you the low levels. This is how you go away and implement it. And hopefully, I won't give away all the facts, because, well, you could dedicate several hours to going over this, but I'll just briefly mention sort of like kind of how I go about doing this, the tools I use to produce what I've produced. So another technique which involves modifying data based basically in sort of like iframes or in images is by is this TPVD, so tri-way pixel value difference. So what they do is they're actually hiding stuff in the iframe, but they look at these things called motion vectors, which I'll sort of get onto in a bit, to look and detect for big differences in the changes of scenes. So where you've got this huge difference when you're going from one scene to another, a scene boundary basically, that's where they're trying to hide their data, because it's just such a rapid change. They're hoping that you won't be able to see, let's say, any artifacts or whatever that's produced. It's going to be very difficult for you to detect because you're changing from one image to a completely different one. So it's going to be very difficult for you to determine what's what. So this is a paper which comes very, very close to what I've attempted to do in terms of its approach. So again, they're trying to use H.264, which is a very, very common technique nowadays for representing video online. 66% at least of online videos use H.264. So what they're doing is these macro blocks can have a type, and basically dependent on the type, they use a 2-bit code to encode different things. So if the macro block type is 16 by 16, they'll encode zeros. They use that value, the macro block of being 16 by 16, to encode the bits 0, 0. So instead of letting the H.264 encoder determine the macro block by saying this is what's best for compression and making the image look the way it should, they change that, and they're using that technique by changing the block type to hide information. So here we get to my project, which is called Steganosaurus. It's and that's the nickname for it. I'll briefly explain why it's got that name. Whenever I've explained steganography to people before, they initially think it's to do with dinosaurs. It's not. They're thinking of Stegosaurus. So it's a bit of a wordplay. But that aside, let's get down to actually what I've actually done and what I've been able to achieve. And this isn't an easy topic to get to grips with. So everything from here on in is very much sort of like on the surface, because this is taking longer. Put it this way: this talk is taking longer than I thought it was, and I've tried to compact everything that I've learned as much as I can and just give you the essentials of it. The honest thing is, you could probably write an entire module on steganography, let alone a 2-hour lecture. So what I've ended up having as my final solution is I've got a command line tool that's written in C and uses this FFmpeg library. But I've also produced a Java GUI which interacts with this command line tool and also uses another library called Zuggler, Zuggler is a Java wrapper for FFmpeg, and I started trying to basically write my entire system in Java, and that didn't work out for reasons which I'll get into shortly. But what we've actually done is we've actually been able to produce something that's capable of hiding a message in video by modifying motion vectors. So a motion vector, and I'll show you this when I get onto the demos, it describes the movements of basically those blocks. When you split an image into blocks, it says this block moves by that much in that direction and that much in that direction. So that's it. It's basically, you've got an X and a Y component which describes the approximate motion of a macro block. So in the beginning, I attempted to write the solution entirely in Java using Zuggler, but that didn't work. That proved to be a complete failure, and that's where I experimented with doing things like trying to change colours of individual pixels to hide information in images. But also another thing that didn't allow me to do is it didn't allow me to change these motion vectors, which is a technique that I found after that's what I really wanted to do. So I had to completely change the way that I wanted to do this, and there were several options if I wanted to stick with Java. One was the Java Media Framework, but this was quite limited in what it allows in terms of, let's say, the codecs and the video types and what have you that it supports. But also, it's more designed at sort of like playback, being able to play back a video and things like that, normal media operations, not trying to do things that, let's say, most video tools aren't designed to do. They're not designed to basically modify things that the encoder's doing, that the video encoder is doing. I could have used the Java native interface, so this allows you to basically execute native functions of like a library or a binary I could have done that to call. I could have written my own wrapper to basically call FFmpeg and maybe use more of the features than what Zugler supported. But the problem was, again, that didn't actually allow me to set the motion vectors, as I found out later on. I didn't find this out when I decided not to use this. But that's something I found out later on. So I then attempted to use FFmpeg to modify a video file, and I did this all in C. And I tried to do it by just linking to the library. So it's a bit like in Java, for those of you who don't know C. When you say, like, import this package, that's essentially kind of what I was doing. I wasn't modifying the source code at that point. But I found that what I actually had to do is I had to modify the source code. Just to explain briefly, another reason why not to use Java for this is that video processing is a very computationally expensive thing to do. And Java runs on a framework. It runs on the JVM, as I'm sure you're all aware. So your performance of your code is limited actually to the performance of the JVM and is capped by that. So there's actually a lot of operations that you can do, let's say in Java on the JVM, which are nowhere near as efficient as they are as if you were to write it in something like C, which is quite a low-level language that runs directly on the processor. So that was another good reason why to move away from Java. But to be honest, if I could do what I was doing in a language, that's all that really mattered. So final solution involved modifying the FFmpeg source code and libraries and incorporating it into the solution that I've done, and modifying the motion vectors but at the right point. So my initial attempts to do this wasn't quite successful because I wasn't trying to modify these motion vectors to the right point. And I think part of the reason behind that, potentially, is the fact that the FFmpeg codebase is nearly 900,000 lines of code long. Trying to navigate your way through that is quite complex when there's encoders for dozens of video codecs, audio codecs, and so on. Trying to find exactly what's doing what and what's responsible for what is a very difficult thing to do. So I eventually got that right, but the macro block type that I mentioned, one thing that I haven't found documented in the literature is the fact that macro blocks can actually, or at least explicitly, is the fact that macro blocks can actually be encoded to say that basically there's no motion vector component. And this is different to saying basically this macro block has a motion vector, a resultant motion vector of magnitude 0. There's actually a difference. So in some cases, what I was trying to do is I was trying to modify the motion vector values, but the encoder had already determined we don't need to record those. So I was making modifications, but those weren't being reflected in my outputted file, which caused things like bits to flip and so on. So that's kind of on a technical and high level how my system works. So what I do is I modify the X component of the first macro block motion vector of each frame, and likewise I've produced another thing, another technique that modifies the Y component. To be honest, I would have done more, and in the outset of this project, I wanted to experiment basically with the different types of ways that you could encode stuff using motion vectors. That was the prime focus. But given how complex video manipulation has been, actually being able to manipulate the video, transcode it, and the fact that there is no real sort of like, a lot of the information that I've presented to you on, let's say, video manipulation isn't easy to come across. There's not a lot of sources, and when it comes to video steganography, there's loads of books which tell you how to do steganography with image files, audio files. I haven't found a single book that tells you how to do video steganography. The closest you get is you'll get a book that mentions that you can do video steganography. But of the ones I've seen, that's as close as you get to them telling you how to do it. They just tell you it's possible. So in my final solution, I use AES encryption again. As Mike mentioned in his email that I'd done some stuff with encryption, I thought that I'd mention this, as it's probably a bit different to maybe what he's covered with you. So this is the current encryption standard, and it has been for, well, in excess of the last decade. So AES was proposed when the then encryption standard was basically deemed to be insecure. These two people defined it, and it became a standard later adopted by the US government. And for them to actually adopt this and decide that it was an encryption algorithm worth using took 3 years. So they started looking for for basically replacements to what they were then using as their encryption standard in 1998, and they only really sort of like decided we'll use this in 2001. And this is basically a summary of the different stages that are involved in it, sequentially from top to bottom. So this should technically be numbered, but it's quite simple. There's very few operations, and it works. You can read exactly how it works here, but basically you're encrypting blocks of text at a time. So you're taking a portion of text, you're encrypting it, you're outputting it. You take the next block, you encrypt it with a key, and you output it. But there can also be insecurities in that, which leads to the whole modes of operation. So this is probably something which is quite new to you, in the fact that this is how block ciphers generally work. They just take a bit of text, they apply a key, and it's encrypted. The problem with that is that you can attack that quite easily. You can build a codebook. You can say, if someone's using so-and-so key, this group of characters encrypts that. That group of characters encrypts that. If you've got enough text and enough encrypted data, you can start to build up a codebook and say, these bits of gobbledygook relate to this plain text. So to avoid that, and this is what my system uses, it uses the cipher block chaining mode of operation. So you have some initial vector, which is basically, it doesn't really matter what it is, so long as you know it, and it has to be known for the encryption process and the decryption process. You XOR it, you do an exclusive OR operation with the plain text, you encrypt it, and you output it. But that is chained, hence the name, to the next block. And what this does is this. So with the aid of Tux here, for the original version, and this is taken from these graphics taken from the Wikipedia page, so feel free to sort of like look there for a more comprehensive explanation. I am literally rushing through this quite quickly because I want to get into the demonstration stuff, because I'm very mindful that we've only got about 10 minutes left. So ECB, which is what I showed you here, which is just the direct encrypting of blocks, you can see the correlation. It doesn't destroy it. Whereas when you use the cipher block chaining, because you're XORing the previous block, it introduces randomness. I believe that has been proven to introduce that. What you're actually seeing is basically randomness. So that's a lot more secure than just using this method of approach. You can spot correlations in the data even if you can't tell exactly what it is. So, in addition to actually just being in addition to what I've done in being able to produce something that can encode in video, I've also produced a number of tools that can sort of like inspect a video. And these have actually proven to be useful when I've actually tried to spot problems in my solution as I was developing it. And now what I'm hopefully going to get onto is a demonstration of exactly what you can do with video. So I've prepared a number of clips, if I can find them. And what I'll first of all do is I should probably show you what a motion vector actually looks like and how it works. So if I can, I'm going to just play you a video and hopefully show you the motion vectors. This is a bit jerky and it is a bit flashy, just to warn you. But if I skip to something that's actually happening, if it will let me, those arrows are your motion vectors for the macro block. So as you can see, you get these sweeping movements where my hand's moving. But there's not a lot, generally, of movement around. If you look at like the desk and what have you, there's very little movement in the motion vectors. Again, this isn't the best example because this particular video player it flickers on and off. This is an open source video player called MPlayer, and there are options which allow you to basically turn on the drawing of the motion vectors. So as you can see with my hand, there's a quite sizable magnitude in the motion that's happening there. Quite an easy way to illustrate this, again, this might be better, is I'm going to show you the exact same video, but what I've done, and this is using my tool that I've produced, I've actually inverted the direction of the motion vectors, and it looks hideous, and it's not hiding anything, but it will hopefully illustrate the concept. So if you have a look, the only thing that's sort of like really changing is the bit that changes, which is my hands. So because of the motion of my hands, you're encoding that as motion. The rest of the macro blocks, you're not really seeing a change. So the clip I showed you in at the very beginning had basically, it had the original version and it had a modified version of that video, and this is the modified version, which was encoding data in the. Sorry, hold on. So it was modifying data in the X components, because I produced two methods, but they're quite similar in their approach. It just depends which direction you're encoding in, and that's the video produced, the one that you saw full from start to finish at the beginning. So I can actually show you how it's possible to produce these, and there is a message. This object file is actually hidden inside the video. So I'm now going to actually show you my application. Now this is a completely cross-platform solution. It will run on Mac, Linux, and Windows. Getting it to do that has been quite a challenge at times, because with it being C, it's not designed to be cross-platform compatible in the same way that Java is. So I would like to hope that this looks quite easy to use, and I would like to just mention now that the bits of paper that I've given you, if you could give some kind of feedback in sort of like how intuitive this looks to use, does it look like it's a hindrance to use it, etc. If you've got any comments or remarks, I'd be interested to hear them. It doesn't really matter. If you think it would be good for me to know it, let me know it anyway, even if it's not necessarily relevant to the question. So by providing an object file, the object file is what I want to hide, and then I give the container the video file to use in the output file. I can select my technique. If I don't know what my technique does, by pressing info, it will tell me. And if I want, I can supply a password. So what I'm going to do for you is I'm going to take, I so hope this works, as I'm doing a live demo. I'm going to take the video that I modified. I'm going to say I want you to output it to, if I go back to the desktop, notice that the only other text file there is object.txt. That was the original message. If I then say I want output, I want it to store it in output.txt. I could then decode it, and it tells me that decoding is completed. Now I'm going to look at this, and what you're going to see is gibberish. Now why are you going to see gibberish? Because what I've done is I've actually encrypted the data, but also I've taken the design choice not to tell the user if they've got the password wrong, because I don't want someone to know if they've got the password wrong that there's a message hidden there or there isn't. That would be quite a bad thing if I kind of gave hints to that. But hopefully, if I've put in the right password, I should get my image back, my message back. This is going to be quite bad if this doesn't work. Well, this is interesting.
Does it overwrite the file, or do you have to delete that?
Good question. Let me try with that one. Well, this is working out to be a brilliant live demo, isn't it? Right. Okay. Well, let's not be discouraged by this. So, if I delete my output, I'll also delete this video. So, let me take you through the encoding process, because it might just be a case that I've got my videos confused, because I literally these didn't exist basically before 9 o'clock this morning, so I've produced these in quite a rush. So if I take the ARS video, and I was working on desktop, wasn't I? So if I call it, no, sorry. Right, so I want my objects, I want my ARS video, and if I call it, again, ARS_X. This time, for simplicity and to avoid typos, I won't set a password, and hopefully it will encode. Hopefully. I'm then going to go back to my decoder. I'm going to pray. It's not usually an obligatory step, but I need to get rid of the password, thank you. And if I decode it, that's what you get. So, that is quite interesting and also very, very embarrassing. So what I've done just basically doesn't work. So, do I have something else that I can show you as a question?
Did that output it? Is that where it outputs it?
Yeah, so obviously there's something not quite happy with that video. What I will show you, though, if I can... Okay, so I'll skip over the fact that that's not actually encoding, which is really, really disappointing. And I'll show you basically some of the steganography stuff. This doesn't work very well on a very small resolution screen, such as a projector, but I think it just about fits if I make this a bit smaller. The problem is like trying to compare two videos visually side to side. You need a reasonable screen. So if I was to take, let's say, the original and the negative, what I can do is I can compare. Let me get something a little bit more interesting, hopefully. There you go. So I can compare the frames either side. I can step through them simultaneously, as I have been doing, or if I wanted, I could look at neighbouring frames from the same video. So that helps to spot artifacts. And the motion vectors, if I just show you a quick comparison. I think what I will have to do is, for the encoding thing, is I think I might just have to leave it as it is, in the fact that it's not working, because I do have other samples that do work, but those videos I don't have the rights to sort of like display them to. They're not my videos, so I won't do that in this lecture. But this tool basically, it allows you to display. If I can hold on. So this just basically displays in a grid. It's not very readable on the small screen, but it just displays the motion vectors, and it allows me to compare them between the two frames, so I can actually see where my encoding is taking place and when it isn't. But if I was to skip to, let's say, a different frame, if I was to find a different P frame, so I should say my technique only works with B frames, but I also use a graphical representation in this tool to display the differences for different components. So I think in the changing the X direction is encoded by green, the change in the Y direction is encoded by blue. So if you get a change happening in both directions, you get sort of like a turquoise colour. So yes, that is the end of my demonstration, I'm afraid, because I've kind of overrun. Does anyone have any questions for me? Sorry, that didn't work out to be quite the length of talk I expected to. I didn't realise I had so much to say. Does anyone have any questions other than the fact that why doesn't that work? No? Right, well, I hope you've enjoyed it. I hope you found it informative. I've certainly found it embarrassing by the fact that doesn't work. But if you could just complete those bits of paper that I've given you with some feedback, and if you could just leave them behind or leave them at the front, that would be very much appreciated. I am going to hopefully try and release this solution later on today via my website, which you've also got the details of, and hopefully make these slides available. That's it. Thank you very much for coming.